This is the third module in a series of presentations that pertain to CCDs and image processing with an emphasis on LSST, and this particular module deals with quantitative image browsing. We'll talk about directory structures and file structures of FITS images, talk about how to browse around in the metadata, the header that accompanies every single image, and edit those values. Think about the pixel data as a two-dimensional array of numbers, and present some examples of how you access, make plots, and browse around in that pixel array structure, and talk about how to use that capability to do CCD performance characterization. The assembly of an astronomical image in an astronomical instrument takes data from two different paths. The pixel data flow off of the imaging array through a signal processing chain to an analog to digital converter, and that digital data is one component in a complete image file that carries the information of flux received by the individual pixels in the array. A separate data path draws information from the telescope control system and adds to this image file information like what is the right ascension and declination to which the telescope was pointed, through what filter are we observing, and other configuration parameters. So collectively, that set of information comprises a complete image file. It's worth talking for a moment for certainly laboratory testing and observations that one takes at a telescope other than LSST, that the directory structure and file names matter a great deal. Our research group likes to organize our data directories by telescope and by instrument, by project, and then we create a subdirectory for every observation date, and then those subdirectories themselves, the subdirectories for each night, contain a subdirectory that holds the raw images, and then each individual processed image as a copy of the file as it's modified through the image processing pipeline. Laboratory data that are taken really are structured differently. Typically, there's a primary hierarchical directory structure that is rooted in the name or serial number of the particular device under test, and then you can have subdirectories that pertain to the different type of laboratory test information that are taken. So keeping track of the bookkeeping, establishing an initial directory structure, and being consistent, that's all a good thing to do. The individual file names, because the file names are accessible at the operating system level to utilities like awk, you can be judicious about what information you include in the file name so that you don't have to crack open the image to learn what's the object name, when was it taken, what sequence number, and where in the processing path down the image processing pipeline that intermediate data product came from. Because images get copied around on the computer, don't ever rely on the directory path. It's important that all file names be unique. Some quick principles about data organization. Always, always, always store multiple backups of the original data and observing logs, ideally in geographically distinct places on different systems. Adopt an organizational bookkeeping convention and stick to it. For science observations, we organize by project and instrument and then by time. So for example, images taken on the UT night of January 3rd, 2015 would reside in a directory called UT01 for the month, 03 for the date, and 15 for the year. The UT in front lets us have file directory and file names that don't start with numbers but with letters instead. So because these things you can get to the file names with tools like awk, making lists of subsets of images is easy to do if you include passband's image type in the file names. Included in the typical data that we take in the laboratory is the type of image that it is. Is it a flat, a dark, an iron 55 image, or what? And then, as I said earlier, as these images proceed through the image processing pipeline, intermediate data products can have file names that are modified according to what stage they're at. If you're executing image reduction by hand, perhaps in preparation of setting up a pipeline data reduction, keep some kind of electronic or hard copy log step by step of what you do, and that includes the parameter choices that are made in the image processing pipeline. So how exactly was the bias subtracted, and what photometric parameters were used for object detection, so that we keep track of the provenance of information that's generated. Astronomical images are typically composite entities with metadata contained in a header and then a separate two-dimensional pixel array of imaging data. In the time long ago when disk space was at a premium, those two components of the images were split apart into a header file and a pixel file, but it's now much more common, thank goodness, to have them merged into a single data structure. The most common file format for astronomical images is called FITS, and it has a long-standing heritage in this community and has a number of advantages. They're essentially binary data files, but the byte order is handled automatically with FITS write and FITS read functions on different operating systems, so that you don't have to worry about binary data file format issues. The header information in FITS files is actually stored as ASCII data, and you would think that you could just go in there and edit it with any general purpose editor, but there's a very rigid formatting structure where that ASCII data comes in certain block sizes. So you can't modify it with an editor and expect to conform to the standard, but there are tools within Python and outside of Python to edit the header information in a standards conforming way. To access the pixel data, there are FITS I/O tools that let you read and write the image array component of each of these images, and that's broadly accessible in C, Python, or whatever. It's common for multi-amplifier CCDs to hold the pixel information in a stack of planes where you think of the two dimensions being spatial X and spatial Y, and there's a third dimension in the image, which is which amplifier is it. Those are called multi-extension FITS files. It's essential with these astronomical images to never do lossy compression on the frames. There is a good tool called FPAC that does lossless compression of the image data, but keeps the header information uncompressed so that you can access it with various command line utilities. So this is just an example of what conceptually a multi-extension FITS data file looks like. There's a primary header which has no image data associated with it that contains a bunch of information that is common to all subsequent extensions in this multi-extension FITS file. And then amplifier by amplifier by amplifier, there's a separate extension with its own individual header and pixel array. The header contains pixel layout information that essentially tells you how to take this single amplifier extension and from it reconstruct the composite CCD image. So there's one extension per amplifier typically, and they have a common 0 extension header that pertains to them all. The information in image headers are keyword value pairs, and this is just an example drawn from, I guess, the CTIO 0.9 meter telescope. It contains what type of image is it, what detector, pre-flash is a configuration aspect of data collection, is it binned or not binned, where do the arrays start in X and Y, how long are they, when was it observed, what telescope, and so on. So there are these conventions for header keywords, and it's important to conform to those keyword conventions because a lot of the astronomical image reduction software presumes certain keywords identify information of interest. The image headers that are produced in astronomy are highly variable. Some of them are absolutely minimalist, and the others are very voluminous with a great deal of information. A typical image header contains time and date of the observation, how long was the shutter open, what filter was used, other instrument configuration parameters, aspects of where the telescope was pointed, what's the air mass, what's the rotator angle, pixel geometry information, how many pixels are there, what is the overscan region, where do the pixels reside in the broader array on the CCD, information that pertains to how are the data taken, initial estimates of the gain in the read noise, what was the temperature, what clocking file was used, coordinate information drawn from the telescope, the right ascension and declination. Some parameters are commonly included that tell you how to map between sky coordinates and pixel coordinates. There are a variety of conventions to do that. One common convention is called the World Coordinate System, and WCS distortion parameters are commonly stored in the headers of images. And as mentioned earlier, this composite information that constitutes an image file is drawn both from the CCD readout system from the telescope control system, and in general from calibration information that you can obtain externally, such as the crosstalk correction matrix. So let's now look down into an image pixel file and think about the type of the data that are stored there. It's commonly the case, in order to maximize the utility of all the bits in the ADD converter, that we use unsigned integer types in these data files, and the exact data type is defined using keywords in the image header. The pixel file typically includes both pre-scan pixels, which are pixels that are digitized before you hit an imaging pixel in the amplifier, and overscan pixels, which are pixels where you intentionally read out beyond the end of the imaging array and digitize phantom pixels, and we'll see as we move forward here the utility of those. There's typically one FITS file extension per amplifier, and these are just arrays of numbers, and with appropriate I/O tools can be read into any numerical analysis toolkit. So the challenge of astronomical image data reduction is to convert the representation of information from flux as a function of pixel ij value into a catalog of detected objects, each of which has a set of attributes of defined parameters. So you should think of that as the image array has the distribution of flux as collected and digitized in the focal plane, and what you want to generate is a catalog where there's an object, a name of an object, its right ascension, its declination, its extent in the two spatial directions, some color information, time variability information, because that's actually something that you can put in a database and use as a basis for doing science. So that procedure entails one or more of the following steps. First, we need to suppress any detector artifacts and instrumental artifacts and convert from the representation of information in the raw image to our best estimate of what flux was actually entering the telescope pupil from each object. The next step is to locally, around every object of interest, determine how much flux is coming from the night sky. That's typically done morphologically in the sense that the night sky has very little spatial structure to it, whereas the sources that we're looking for are compact objects. Then, using some well-defined detection criteria, after doing some kind of optimal spatial filtering, you go through the process of detecting sources. That detection step, essentially what parameters you choose depends on the tension between two things. If you want to generate a catalog of sources that is pure, in the sense that there are no false detections, you'd set the detection threshold very high and apply very stringent conditions. The downside of that is that you're losing faint sources that are down near the detection floor. On the other hand, if you want to have a catalog that is complete, that captures every single source that's more than 3 sigma significant, you'd set the detection threshold lower, but the penalty that you pay there is, along with that complete catalog of sources come spurious detections that are not real. So identifying where you want to be on the receiver operating curve of source detection is one of the knobs that can be turned in any image processing pipeline reduction of astronomical images. Anytime you look at the sky in different seeing conditions, the very definition of a source becomes a slippery idea, because in poor astronomical seeing conditions, sources will merge together and you can't distinguish that it's a composite object. And if the seeing gets much, much better, suddenly they get resolved into two different things. And so the aggregation of individual detections across images taken at different times into a clear representation where the primary entity is the source on the sky is a non-trivial task. Another step in this image reduction process is to try to make a mapping between pixel space in XY and right ascension and declination on the sky. Then for all the sources that we have, based on the flux that we see and their shape, 3 different types of astronomical measurements are made on these sources. Photometry is the measurement of the flux that has arrived at the telescope pupil from that source. Astrometry is the measurement of the position of that object in the sky in some right ascension declination coordinate system. And another thing that we're going to do with LSST that does not have a conventional name in astronomy, I'm going to call shapeology, which is the careful measurement of the two-dimensional distribution of flux for the point spread function for unresolved sources and the shapes of galaxies as resolved sources. And that's the foundation for all weak lensing measurements that we're going to make with LSST. We then need to apply appropriate calibration methodologies for flux and position and shape measurements. It's common to go back and add fake sources to the images and rerun the reduction pipeline in order to map out the detection efficiency for finding objects of different size, shape, and position. The step of aggregating the detections across different frames into composite objects that we think are real sources on the sky can be done either by taking the catalog image by image by image by image, or doing a simultaneous fit across all images to basically derive optimal estimators for object attributes. In order to look for variability over time, a common thing is to actually subtract images taken at different times. With an appropriate subtraction methodology, sources that are not variable are suppressed, and variable sources are the only things that survive in those difference images. An alternative image reduction approach is to actually take some subset of the images, register them with one another, compensate for point spread function differences, and stack them all up in coad so that you drill down, improving the signal to noise ratio prior to the detection step. So this is a complicated methodology, and a prerequisite for all this is to really understand the different image artifacts and CCD artifacts that can corrupt the data, and that's really the thrust of what we're talking about in this set of presentations. There's an array of image visualization and analysis tools that we've inherited from decades of development effort in the astronomical community. And just so people understand some of the buzzwords that are used to describe these different tools, we can start with IRAF, which was written by the National Optical Observatory around the 1980s. It's still a standard at many observatories. It's free software, and many quick look image reduction utilities at long-standing observatories use the IRAF toolkit. Around the year 2000, the community some subset of the community made a transition to IDL, which is a commercial image processing framework. It has an entire suite of astronomical image reduction analysis tools. The licensing for IDL costs money. There's a Python version of open source software that are, in some cases, replications of the toolkit within IRAF, in other cases, philosophically distinct approach, because it's astronomical toolkit built on Python. By and large, that's free open source software. LSST is in the process of developing Python-based image reduction tools. That goes by the name of the LSST DM stack, or the DM stack, or the LSST stack, and that's an open source suite of Mosaic CCD image reduction tools, and we'll move in the direction of understanding that as we move forward here. There are also standalone codes that do individual components of pipelined image reduction, and you'll hear people refer to these, and so we might just spell out what some of those are. If you have produced flat-fielded images, there are standalone tools that will go into those images, identify sources, and extract positions and fluxes. Some of them use analytic representations of the point spread function. Others use sort of empirical distributions of the point spread function. DuPhote, DAOPhote, and Source Extractor are examples of standalone photometry codes. The positional aspect of things is dealt with by frequently taking the images and warping them onto a pixel grid such that each pixel subtends an equal angle on the sky. That almost invariably introduces correlations between pixels. One of the tools that's common for doing that is called S-warp. There's another very powerful utility that people should know about called astrometry.net, and what that provides is the ability to upload any image to this URL, and it uses a catalog of known sources in order to return to you the center of the image in right ascension and declination, along with some preliminary distortion estimates. So that's a powerful thing. WCS tools is a suite of command line utilities that use the image header to flip back and forth between pixel coordinates and right ascension declination coordinates. It can also be used to explore and browse image headers online from the command line. DS9 is a commonly used image visualization tool that also allows you the ability to make simple horizontal and vertical cuts across images. What we want to focus on here is the task of what I would call quantitative interactive image browsing, which is essentially sniffing around in an image using a combination of pixel statistics evaluation, making one-dimensional plots of interesting quantities, and looking at two-dimensional visualizations of the imaging array. It's an acquired skill, and iterating between those different visualizations and representations can allow you to drill down and understand some of the gremlins and artifacts that we've described previously. And so we'll go through in this presentation quickly setting up the framework to help people think about how to do that, and then move into a Python-based example of doing it using an example FITS file. So each LSST CCD is about 4,000 by 4,000 pixels, segmented into 16 different readout amplifiers. The wavefront sensors are half as big, have 8 output amplifiers each, and are a 2,000 by 4,000 array. It's always the case in the raw images that are generated by the LSST Laboratory CCD Characterization Toolkit that the very first pixel that is read out in time is the lowest index pixel in the data array. Exactly how that geometrically maps onto the two-dimensional CCD structure is vendor dependent. And at the current time, we have 2 different vendors in play for LSST detectors, and they chose to implement the 16 amplifier layout differently. In one case, the bottom amplifier structure is reflected up onto the top side so that the amplifiers don't reside in the same spatial corner of every image. The other vendor essentially did a rotation of the mask structure, and so the way the 1 pixel appears in the actual CCD mosaic depends on which of those 2 layouts are actually underlying the chip that's being looked at. We do have documentation on all this, and this information is in principle contained within the image header of each segment. There are other differences between the CCDs from these 2 vendors. In one case, there's a 2-stage output amplifier, in the other case, a single stage. One is 4, the other 3 phase of parallel clocking. In one case, there's this midline bleed stop, which is meant to prevent charge above full well from streaking all the way into the other half of the array. The pixel layout format is slightly different in terms of how many pixels there are in the serial and parallel direction, and whether the clock voltages that are applied are unipolar, only voltages greater than 0, or bipolar, meaning both plus and minus voltages, is also different between those 2. So there are some slight differences between them. This is the format of a single amplifier image. So this is one of 16 amplifiers on a CCD. And you should think about the readout amplifier sitting down here in the bottom left corner. And if you ask, how do I know that? It's because I know the number of pre-scan pixels, which are the non-imaging pixels that are read prior to hitting the first pixels in a row. The number of pre-scan pixels are significantly less than the number of overscan pixels over here on the right-hand side. So I can tell where the readout amplifier is by picking the side of the serial register that has the fewest number of pixels that don't contain any light. So this is the row direction. The amplifier is in the bottom left corner. This row is read first, and then sequentially, rows higher up in the image are read out later. So the charge flows down and then to the left. The number of pre-scan pixels, the number of overscan pixels, and where this image resides within the detector are all described with a set of keywords and values that reside in the image header for this particular segment. And in the nomenclature of Python, the first element in the pixel array is element 00. That's the first one read out. It's always the case that in a single detector, all pixels that share an index are digitized at the same time. and that's important in order to do crosstalk correction. We typically have 20 or so overscan pixels in the serial direction and about 45 rows of overscan in the parallel direction. This is just an example of what the 0th extension image header looks like for a frame taken from a laboratory CCD test stand, and we'll look at that in a little more detail when we go into the Python example, but you can see it contains dates, times, what CCD it is along with its serial number, what type of image. This is a flat, so it's a uniform illumination test image, temperatures, filter names, control file configurations for the CCD readout system, a first cut at the gain and read noise in this extension, and on down the way to configuration information for the monochromator and so on. A single extension now for an amplifier header contains information that's only unique to that extension, and it's in particular, where does this amplifier segment reside within the broader CCD is the primary information of interest there. The overscan pixels are extremely valuable in the characterization of the performance of a system. So I'll remind you that these are pixels that we digitize by reading out past the end of a row and reading beyond the last row, so that these are pixels that are, if you want to think about it this way, phantom pixels appended to the image. And because those pixels have no flux in them, that's a good place to go to measure the read noise. And so in any image that has an overscan that's reliable and that's not polluted by trailed flux from bad charge transfer, you can look in the overscan to determine the read noise in A to D converter units just by taking the standard deviation. In order to convert that read noise into electrons, you need to know the gain in the signal processing chain, the conversion between ADUs and electrons. The overscan region is also the place to look to determine the bias, the offset voltage that we introduce to allow us to get away with unsigned integer data representation. And so looking in the overscan to find the bias is a standard trick. Whether you use a single scalar number and subtract that from the array, or whether you subtract a row-dependent bias, or whether you subtract an entire bias array from the image, depends on the nature of the stability of the flux-free DC component pixel by pixel. And that's something that needs to be explored, and they need to make a judicious choice of what to do there. The roll-off of flux as you move into the overscan can be used to measure the charge transfer efficiency, because the first pixel in the overscan of every row, the only flux in that pixel comes from residual trailed flux that wasn't properly transferred as the charge was moving to the left in the serial transfer. And we use that extended pixel edge response in order to measure the charge transfer efficiency using laboratory data from LSST chips. Even during operation when LSST is on the sky, monitoring the overscan region in every single image and verifying that the read noise is a sensible value, that the charge transfer efficiency hasn't degraded, measuring the bias level and so on, is a good housekeeping thing that we certainly intend to do. So turning now to thinking about interrogating individual pixels in the array, especially using Python, I'll just make a couple of quick comments. Indexing of arrays in Python is zero-based, so the first element in an array is index 0, 0. You need to be very careful about the fact that in Python, the first index is the row of the array, and the second index is the column of the array. And if you put up an image in an image visualization tool, your inclination is to think that the horizontal direction would be X, which would be the first index, but that's emphatically not the case. Python thinks about it from the standpoint of rows and columns. So the first index in Python is moving vertically in the image, and the second index in Python is moving horizontally in the image. Another cautionary note is, because we do sub-pixel determination of centroids, we make a conceptual conversion from having sort of pixel information be single integer values to a continuum representation, where I think of position in the row and the column direction as a continuum variable. So I could have a position of 1.356, and that's a well-defined thing. But there are different conventions in how people make that discrete to continuous transition. So if we identify pixel 1, 1, pixel location 1, 1 as this red dot, in some conventions, the origin of the continuum pixel coordinate has the first pixel in the array corner here be 0, 0. So the location 1, 1 is at the intersection between 4 pixels. In other conventions, pixel location 1, 1 is at the center of the first pixel. And in yet other conventions, pixel location 1, 1 can be the innermost corner of that first pixel. So even the origin, not just the orientation, but the definition of the origin of pixel coordinates is not a well-defined thing. The other option is that you think about the origin as being the bottom left corner of the array. So for LSST amplifier segments, the first element in the array is always the one that's physically read out first. And I'll just caution you that those different astronomical image processing tools that I mentioned earlier, IDL, IRAF, Python, and so on, source extractor and IDL, use different coordinate conventions. And there's a nefarious problem as you take data from one standalone tool and move it into another standalone tool about what implicit assumptions are made about the origin of the continuous pixel coordinate system. And there's this 1 pixel, half pixel ambiguity that rattles around if you're not careful. The other point to make here is that the image header pixel conventions about the bias section and data section in the array do not conform to Python's indexing conventions. So these data and bias section image keywords are in IRAF coordinate convention, where pixel 1, 1 is at the bottom left corner of the image in a right-handed coordinate system, with the first index being the X direction along the serial register. So there's sort of a hardwired convention in the heads of most astronomers that the X direction is along the serial direction of a CCD array data file. Once the data are read into a Python array, you need to worry that the convention is flipped and keep track of the fact that it's 0 index based and that it goes row column. And oh, by the way, just to make life even better, there's an entirely different coordinate convention for the physical location in the focal plane of the LSST camera. And to make things even worse, the telescope adopts a different coordinate convention for where the light lands in the focal plane of the telescope. So that's unfortunate, but it is in fact the case. There are a number of references that you can get to that are essentially Python-based image processing tutorials. And in the next component, in sequence 3.5 here in our next module, we'll do some examples using Python to crack open a FITS file, interrogate the header, pull out pixel values, make row and column plots, and look quantitatively at some of the CCD features that we described earlier. We'll learn how to average multiple rows and columns together, look at the bias stability, take a spatial Fourier transform to look for periodic structures in the array, and finally make a bias subtracted trimmed image of a single amplifier segment. So turn your attention to module 3.5 and we'll do that.